Hello everyone, and thanks for watching Edupedia World videos. In this video, we begin our study of quantum mechanics, which comes from the dual nature of light. So let's look at what classical mechanics has been up till now. In classical mechanics, the most important quantity regarding any physical object is the state. And the state is basically a mixture of all the variables required, the values of all the variables required to completely determine the way the object behaves. So for classical mechanics, the state of a particle is given by the position and the velocity. So for a single particle, let's say r, which is the position, and r dot, which is the velocity. In that case, you know everything there is to know about the particle, and you can determine everything else. For example, you can determine the kinetic energy, which will be given by half m v dot v, or half mv squared. You can determine the angular momentum, which will be determined by r cross mv, and you can determine all other quantities, because every other quantity is basically created by the position and the velocity. And how are you able to find r of t? Generally, you are given the force and you use Newton's second law, F is equal to ma, and using F is equal to ma along with some initial conditions generally, you are able to determine r as a function of t and v as a function of t. And obviously, dv by dt will be the acceleration, the kinetic energy will be half mv square, and so on. In the case of quantum mechanics, it's slightly different, and the biggest difference comes from the fact that the state is a completely different thing. And this is why initially beginners often have trouble understanding quantum mechanics properly, because they are so used to the idea of a state being defined by the position and velocity. In quantum mechanics, the state is defined by something completely different, which is denoted by psi and is called the wave function. So just like pretty much in every classical mechanics question, our solution boiled down to finding r of t and v of t. And after finding r of t and v of t, we will be able to find whatever it is we need to find, like kinetic energy. In quantum mechanics, what we need to find is psi. Now psi is a wave function, and generally it is a function of x and t both. Or if it is in 3 dimensions, x, y, z and t. But for the beginning of quantum mechanics, we'll just assume that motion is in 1 dimension. So we have x, which is the position, and t, which is the time. So psi of x of t is a function. A bad example could be 3x squared plus 2t or something like that. This is not a proper wave, but I'm just giving you an example. So psi of x of t will be a function of x and t, and once you find psi of t, you know everything there is to know about the particle. And just like using r of t and v of t, you can find angular momentum, using psi of x and t, you can find everything there is to know: the position, the velocity, the angular momentum, the kinetic energy, the torque, and so on. So this is the fundamental problem in quantum mechanics, which is you need to find psi of x of t for whatever particle, and that gives you the state. Remember, the state is a collection of variables that tells us everything there is to know about the particle, which means by definition psi of x and t tells us everything there is to know about the particle. Every information that we know or we can derive about the particle is encompassed in this psi of x or t. By the way, I shouldn't be saying particle because it can be a particle or a wave. It has obviously dual character, but the state is represented by psi of x and t. Now how do we find psi of x comma t? We have to solve what is called the Schrodinger equation. And the Schrodinger equation is given by iota h del psi by del t is equal to minus h square by 2m del square psi by del x squared plus V of psi. V is the potential energy as a function of x. So I should write Vx. Right. So del psi by del t is basically the partial derivative. You'll have studied partial derivatives in your mathematics course, but in case you haven't, del psi by del t, where psi is a function of both x and t, is basically the derivative with respect to time, assuming that the position is constant. So for example, if you had psi of x comma t is equal to 3xt plus x cubed t squared, then del psi by del t will be given as, we just assume x is a constant and differentiate with respect to t. So 3x plus this will be 2x cubed t, and similarly del psi by del x will be, we differentiate this with respect to x assuming that t is a constant. So this will be 3t plus 3x squared t squared. And the double derivative with respect to x, del squared psi by del x squared, which is what we need in this equation, will be simply 6xt squared. So when we said that in classical mechanics we need to find r of t and v of t using the equation F is equal to ma, then F basically told us how the particle moved. It was the extra condition that we needed to require, and then we used Newton's second law and found out the acceleration and hence the position and velocity. So this is the analog of Newton's law. It's not exactly like Newton's law, but this is the analog in quantum mechanics, meaning that it tells us the state of the particle. Here the state would be r of t and v of t in classical mechanics. In quantum mechanics the state would be psi of t. And this equation tells us the state of the particle based on the extra condition, which is V of x, the potential energy as a function of displacement. Yeah, potential energy. So, and we know the relation between potential energy and force. If you know the force, you know the potential energy and vice versa. So, once we know the potential energy, this is the simple equation which determines psi of x comma t. Now, one of the problems in quantum mechanics is that this equation for complicated values of v of x can turn out to be incredibly complicated. And so the mathematical solutions to quantum mechanics problems only exist for a few basic problems. There are few basic simple problems where v of x is simple enough that you can actually solve psi of x of t completely, and after finding psi of x of t, find everything that you need to know about the particle, such as its angular momentum. But there are some simple cases where you can solve it, but for complicated cases you have to find approximate solutions, and that's a whole different study of advanced quantum mechanics, which is how you find solutions to complicated problems. We'll not delve into that a lot. We'll try to solve the Schrodinger equation for a few simple cases, such as a particle in a box or a harmonic oscillator and so on. Now, right now we'll focus on the fact that once you have found psi of t, how you're supposed to get the position, the velocity, the angular momentum, and so on. In a later video, we'll try to focus on how you get psi as a function of x and t using this equation. So right now, let us assume that we know v of x. From that, we were able to solve the Schrodinger equation, and we were able to find the function psi of x comma t, which is the state. Which means everything else about this object should be able to be determined from psi of x comma t. So the first step is where the object actually is. When you know the state of a particle as r of t and v of t, you know exactly where the particle is. The particle is at this position. At any time t, you have a position vector r, that is the position of the particle at time t. Now what is the position of the particle at time t if the state is psi x comma t? That is a really profound question, and that is the basis for the difference between quantum mechanics and classical mechanics. So in quantum mechanics, we do not exactly know where the particle is. Now keep in mind, the state tells us everything there is to know about the particle. There is no information beyond the state that we would need to get the position. But even the state, even psi of x comma t, does not completely tell us the position. Meaning, according to quantum mechanics, there is an intrinsic uncertainty when it comes to position. You could know everything there is to know about an object, yet you would not know exactly where the object is. Right. So there is a statistical interpretation which basically says that the integral of a to b mod of psi of x comma t. By the way, in case you notice, we had an iota in the Schrodinger equation, so the solutions can be complicated as well. So integral of psi of x of t mod square, which is psi into psi star dx, this is basically the probability of finding the object between a and b. So let's draw a function also at a particular time t. At time. So if you fix the time, psi of x of t just becomes psi of x, which is a function of x. So let's say the function is behaving somewhat like this. Let's say this is point A, this is point B. Then if you integrate the mod square of the function, that means you multiply the function by its complex conjugate, so the mod of x is obviously a real number, and we know that because the position has to be a real number. Right. By the way, position and other things which we'll try to find out are called observables. So in classical mechanics, the state itself is an observable because you can measure the state. In quantum mechanics, the state is not an observable. Observable are things you measure in experiments such as position, velocity, angular momentum, and these are derived from the state. In turn, the state is derived from the Schrodinger equation, in which you have to input v of x. Integral of mod of psi x squared, let's say this is mod psi x squared. Right, this is not the graph of psi of x. Psi of x can be positive, negative, complicated. This is the graph of mod psi x squared. Then the integral between a and b, which means this whole region, is the probability of finding the particle between a and b. Notice the intrinsic uncertainty in quantum mechanics. Even if you know psi of x of t completely, you do not know where the particle is, you only know the probability of where the particle is. If you took a small region near b, let's say b minus delta x, b plus delta x, and only integrated this, that would give you the probability that the particle is near point b. If this is, let's say, a point c, then you integrate near c, you will get the probability that the particle is near c within the interval of integration. Now you can see that mod psi x whole squared has a much higher value near b than near c, and it has an almost zero value near this point d. That means the probability of finding the particle near b is much larger than the probability of finding the particle near c, and the probability of finding a particle near d is approximately 0. If you have a big range in between, you want to find out the particle, let's say, what is the probability that when I measure the position of the particle, I find it to be somewhere between a and b, the probability will be integral of a to b psi of x squared dx. And at a particular time t, you just treat the time t as constant, right? And psi of x of t becomes psi of x, just the function of position. Now, one of the important things here is that when you measure, the wave function completely changes. So for example, let's say a particle is in some state psi of t, where mod psi x squared graph is given like this. And let's say now you perform an experiment and measure the particle. And you find the particle is at point A, let's say. You find out the position and it comes between an interval near A. Now what if you make the observation again and you again try to calculate it? Well, the second time you do it, you will find it at A. Otherwise, there would be no sense in measuring, right? If you calculate the position of a particle and immediately after you calculate it again, you expect it to get the same position, because otherwise the position would be indeterminate. Notice there's a difference between indeterminate and uncertain. The position is uncertain, but it is completely determined. We know what the particle's position is. It has a certain probability of being between A and B, certain probability of being near C, and so on. So what happens is, And this is the difference between quantum mechanics and classical mechanics. Every time you make an observation, every time you perform an experiment and measure something which is called an observable, you change the state. So if a particle is in state psi and you measure the position, the simple act of measuring the position, which will probably be by shining light on the object, will change the state of the particle. The act of measuring momentum will change the state of the particle. The simple act of a measurement itself is enough to change the state of a particle. So initially if it was like this, and then you measure and statistically by chance you find it to be at A, then at the very next instant the wave function will change. Now the wave function will be like this. You see that it has a high probability of being found near A and a nearly zero probability of being found anywhere else. So the wave function was moving along on its own accord and it had a particular structure. The most probability was finding the particle near B. You measured, you happened to find it near A. The simple act of that measurement changes the wave function from this thing to this thing where it's non-zero everywhere and it's zero in the vicinity of A. Now if you again measure, you can see that now the particle has basically a non-zero probability only of being measured near A and a zero probability of being measured anywhere else. So our measurement is consistent. If you have a particle in a certain state and you measure the position and you measure the position again, it will give you the same value. But the act of measurement of the position itself will change the state of the particle such that the new state will tell us that it is near A. And after you measure it, if you let it go again, it will continue evolving along according to the Schrodinger equation, which is basically has both x and t components. So immediately after the measurement, it will be this spiked value near A, and then it will start moving again according to its own accord, according to the Schrodinger equation. This process, by the way, is called the collapse of the wave function. So we see two different kind of processes in quantum mechanics. There are ordinary processes where the Schrodinger equation determines the psi of x of t, psi of x and t, and it changes with time and position according to the Schrodinger equation. And then the other type of process is a measurement in which you actually calculate the value of an observable, and that changes the state of the object immediately. The moment you measure it, you have changed the state of an object. Now, notice that this is completely different from classical mechanics. In classical mechanics, you could measure the position of an object r of t without changing the position, without changing the velocity. But in quantum mechanics, the moment you measure, you change the state of the object. Another important thing in quantum mechanics is the concept of normalization. So when we say that integral of a to b mod psi of x of t whole square dx is the probability of finding it between a and b, finding the object at time t. Remember, the LHS is a function of time. Between A and B, then obviously the probability that the particle would be somewhere in the universe would be 1. So if we change these a little bit and the limits instead of A to B, we make the limits to be minus infinity and infinity, then this is the probability of finding the object at time t between minus infinity and infinity. But this has to be equal to 1 because the particle obviously will be somewhere between minus infinity and infinity. So there is a restriction on wave functions, which is why initially when I wrote a random wave function, I said this is not a real wave function, because a real proper wave function will always have to be normalized. That means the integral from minus infinity to infinity will always have to be 1. But we need to make sure this is continuously valid as long as the wave function is evolving according to the time-independent Schrodinger equation. Fortunately, there is one proof which I'll do right now, which shows us that if the wave function is normalized at any particular time, it is normalized for every point thereafter according to the Schrodinger equation. So if you are able to find the solution of a Schrodinger equation and that solution is normalized, then it will stay normalized for all possible time. Another important thing, which is a condition for normalization to be true, is that psi of x comma t has to go to 0 as x goes to plus minus infinity. Meaning the probability of finding it at infinity should be 0, only then will it be normalizable. If a function extends to infinity and does not go to 0 as x goes to infinity, then you cannot even calculate the integral from minus infinity to infinity. Right? For example, if psi x is x square, then you cannot calculate the integral from minus infinity to infinity. So for psi to be normalizable, this condition has to be true. Psi x should go to 0 as x goes to plus minus infinity. Now our goal right now is to prove that if the Schrodinger equation is normalized, if the wave function, which we get according to the Schrodinger equation is normalized at some time, it will stay normalized for all further time. So let's rewrite the Schrodinger equation in a slightly different form. It can be written as del psi by del t, I'm just taking a few things towards the right, is equal to iota h by 2m del squared psi by del x squared. Now I'm not going to write del psi of x comma t anymore just for the sake of convenience, minus iota by h v psi. Now another important thing which I may have forgotten to mention, h is not the Planck's constant, it is the Planck's constant divided by 2 pi, and it is often called the reduced Planck's constant. And there's a line over the h which denotes that it's reduced. So this is del psi by del t. Now if we take the complex conjugate of this equation, we get del of psi star by del t, that is equal to minus iota h by 2m del squared psi by del x squared plus iota by h, so this is psi star, v psi star. Right. And now what we need to find is d by dt of integral of minus infinity to infinity mod of psi x comma t whole square dx. Now this whole thing is only a function of t. That's why we wrote d by dt. But we can actually take the derivative inside and apply it on mod of psi x squared, but then it will become a partial derivative because this is a function of x as well. So this can be written as integral of minus infinity to infinity del by del t of mod of psi comma x comma t whole squared dx. Right. So we need to calculate this thing first, del by del t of mod psi squared. That is del by del t of psi star into psi. And that can be written as psi star del psi by del t plus psi del by del t of psi star according to the product rule. So we need to calculate this thing and we'll use these two equations. We'll multiply this by psi star, multiply this by psi, and add them, and we'll notice that this term and this term will get cancelled. And what we are left with, del by del t of mod psi squared is equal to iota h by 2m psi star del squared psi by del x squared minus psi del squared psi star by del x squared. Now this can also be written as del by del x of iota h by 2m times psi star del psi by del x minus psi del psi star by del x. Right, so this is this thing del by del t of mod psi squared. What we need to find is the integral of this from minus infinity to infinity dx. So we just integrate this from minus infinity to infinity. That means we can remove this and we can directly put the limits because this was the derivative, minus infinity to infinity. Now we know that psi goes to 0 as x goes to infinity. It also goes to 0 as x goes to minus infinity. Similarly, psi star, which is a complex conjugate, also has to obey the same thing. It goes to 0 as x goes to infinity or minus infinity, which means this whole term is 0 because both the terms at both the endpoints are 0. So this is what we've been able to prove, that the derivative of the integral from minus infinity to infinity is 0, meaning the integral from minus infinity to infinity remains constant. So if we are able to find the solution of the Schrodinger equation at some point and then multiply it by a constant to make it normalizable, then for all the rest of time it will continue to stay normalizable. How do you normalize a wave function? If you have an unnormalized wave function, you calculate minus infinity to infinity psi star psi dx, and let's say this is equal to some quantity a. Then all you do is you divide this by a, and then this will be 1, which means that the new function will be psi by root a. Right, and the complex conjugate will be psi star by root a, and then you integrate it, then it will be normalized because the integral will be 1. If it is normalized at time t is equal to 0, it will continue to stay normalized for all time to come. This will be the conclusion for this video. In the next video, we'll further our discussion and we'll try to find out how you calculate the position and momentum given psi of x comma t. Right now we saw how you calculate where the probability of finding the particle at some point between x and t. The next time we'll see how to calculate the position and the velocity or momentum, and then from that we'll be able to calculate every other thing as a function of psi of x comma t. I would like to repeat one more thing that I said at the beginning, which is why students have a lot of confusion. Psi of x comma t is our ultimate goal. We find psi of x of t, we can find everything that we need to know. Now, that does mean we can find everything because everything may not be possible to be known. There might be an intrinsic uncertainty. Everything that can be known can be determined from psi of x of t. Psi of x of t is determined by the Schrodinger equation. We'll see that a little bit later on. Right now our focus is once we have psi of x of t, how do we determine it? Determine other physical quantities like position, momentum, kinetic energy, and so on. Thank you.